Thanks. Let's begin with a word of prayer. Dear Heavenly Father, we thank you for this day, just another day to celebrate your creation. We thank you, Lord, for being an awesome God that you are each and every day. We thank you that you love us even when we don't love you. And we just thank you for your grace and mercy for us each and every day, Lord. In your name I pray. Amen. Talking about the result of continuous differentiability, or we could call it continuously differentiable functions. What I want to talk about, the result. Now, so let me just state the theorem. You know, if V and W are normed linear spaces, and if F is a function, say from V to W, let's see here, and partial F, well, a little bit more. And let's suppose F is equal to a sum, beta, V1, Vn, basis for V, and gamma, W1, Wm, basis for W. All right, where F is equal to a sum, j equals 1 to m of F. Let's see here. I'm going to put the j upstairs for the sake of the. It's just a nicer notation for this particular problem. F upper j, w lower j. So this is the expansion of f into component functions. So here's our setup, and if we have, in addition, that partial f j partial xi are continuous, near on an open set. Let's say U containing A. All right. So A is an element. A is an element of U, which is a subset of V. All right. So we've got a function from one normed linear space to another. We've got basis to set up the formulas. F sub j is the jth component function of f, and we're assuming that the partial derivatives of each component function with respect to each variable in the domain x1 through xn are all continuous on some open set. All right. All of this that I've said is what is meant by continuously differentiable. F is said to be continuously differentiable if it has partial derivatives which are continuous on some open set around the point in question. So this would give you continuous differentiability at A. Means that there exists some open set around A on which the partial derivatives are all continuous. If you have all of this, then F is Frechet differentiable at let's say x equals to A, and the Frechet derivative at A of f on the sum of, let's see here, I equals 1 to n of hi vi is equal to a sum I equals 1 to n sum j equals 1 to m. And so we have a h sub I partial f. I guess I don't need to put the j upstairs here. I'm sorry about that. I'm going to chicken out and put the j downstairs for now. Okay. J. partial xi, and then wj. Okay. So, proof. First point here in the proof is to notice that we don't need to prove this for the entirety of the function, all right? So in particular, the vector limit property implies that the differential at a of f when it exists is just equal to dA, well, goodness gracious. Sorry, I have made my, I have to face the basis here, all right? So dFA of h, let's say, is equal to a sum, j equals 1 to m, of dA f sub j, this thing, acting on h times wj. I'm trying to just go just a little bit past where Edwards does and give you a proof for a normed linear space here, because I'd like to use this result for a normed linear space, but this is I promise, this is the last hurrah. This is where we're going to stop talking about theorems for normed linear spaces. All right, this is it. Enjoy it. We're about to go to Rn as soon as this is done. And maybe I should do it here. But my point here is to get the Frechet differentiability of big F, it suffices to have the Frechet differentiability of each of the component functions, and then you just string them together in the appropriate vector, and that gives you the derivative for the whole thing. All right. So to outline the proof of the theorem, if we can prove this theorem for one of the component functions, then we can just piece it together and get the theorem for the whole kit and caboodle, right? So we'll focus, specialize to f. Now I could use an f sub j, but we're just going to make little f equal to f sub j as to not write f sub j a billion times, okay? If that's all right with you guys. We're going to look at f equals to little f sub j and try to prove the theorem for this. So then f is a mapping from V to what? To R. And we're going to try to prove the result for that. And also, we assume that the basis for V is such that the following holds. So if I have the norm in V of, let's say, xj, vj, I'm going to assume that the norm and the basis is such that the norm of the jth component vector component is less than or equal to the norm of the whole thing. Right? This is certainly true in Rn, right? If you take like the length of one of the vector components of a vector, it's smaller than the length of the whole thing put together. That's only true though if you take orthogonal vectors, right? But we need that at one point in this argument. This does assume basically a sort of orthogonality of the basis. We're going to prove it with respect to the orthogonal basis, and then the update I'm posting to chapter 3 shows you that if you prove it for an orthogonal basis, it automatically transfers to automatically transfers to other bases by a simple linearity argument. That's one of the problems in your homework. Not all that, but a piece of that, an important piece of that. All right. So, all right, now we want to look at, we want to show that, what are we assuming? So we're assuming that partial f, partial x1, partial f, partial x2, partial f, partial xn are continuous near, well, let's say on, come on, erase, on U, which contains some point A. All right? So we're going to assume the continuous differentiability of the little function f. All right. Now, the next step in the proof is to, it's kind of sneaky, all right? It's kind of sneaky. And so it's, well, I think I remember. So, oh, I better not. If I remember something wrong and then this devolves into the whole class, that would be a shame, because this should really not take us all of class. So let me behave, follow what I did. So basically, I'm just adapting the proof of Theorem 2.5 on Edwards, page 72, for a normed linear space. So here's the setup. What's our goal? Our goal is to show that df at the point A, defined by, some I equals 1 to n of hi partial f partial xi at the point A, to be more specific. All right, these are evaluated at the point A. I should really say that. That to show that this is indeed satisfying the Frechet quotient, the Frechet limit, let's say. It's clear that if we make that our definition of df, daf, right, or L, if you like, I was calling this quote unquote L of h in the definition I told you guys the other day. Is it clear that that's linear in h? Yes. Because if I had h1 plus h, if I had h plus k, you just get, it's not hard to see that this is linear. So it's a linear transformation. The question is, does it satisfy the necessary difference quotient, right? So what should we look at? What essentially we have to look at, what we have to investigate is the change in f at the point A. Well, let's say let me just call it change in f. Edwards has a more specific notation for change in a function at a base point, but I forget which point he puts on it, so let me not try to do that. Okay, so f of a plus h minus f of a, that's the thing that we're trying to understand as deeply as we can, okay? Because ultimately what we have to show is we have to show that the change in f minus daf of h divided by the norm of h tends to 0, right? That's what is meant to show the Frechet quotient. The change in f is well approximated by the differential of a at f acting on h, in the sense that as h goes to 0, that quotient goes to 0. So what we got to do is to study this difference, all right? And here's the sneaky thing is, what you do is to look at the h as being built from, here's the sneaky step. So what we do is h is equal to, well, first of all, it's equal to what? It's h1v1 plus h2v2 plus plus hnvn. That's what h is. H is in the vector space v. All right, so we're going to say that h sub naught is equal to something. We're going to say h sub 1 is equal to something. Let's see, what's h sub naught going to be? H sub naught is just going to be 0. H1, what's it going to be? Oh, see, and I can't use this notation quite. I'm going to have to, you'll see why I can't do this. I'd like to just say H1 is equal to H1V1, but that's ambiguous. So to remove the ambiguity, I put a vector over this just to not be annoying. All right. Because H1 is a scalar in our notation, whereas H1 vector is a vector. So in other words, H1 is a scalar component. H1 vector is actually the vector component of H in the one direction. What's H2? I think you see where we're going with this, right? What's Hn? In fact, it's just H again, right? Okay, so what we do then is we have f of a plus h minus, well, I'm setting myself up for the, so the change in f is what? It's f of a plus h minus f of a plus h n minus 1 plus f of a plus h n minus 1 minus plus f of a f of a plus h1 minus f of, oh, excuse the other way around, minus plus, right? Plus f of a plus h1 minus f of a. So you could think about a picture, three-dimensional picture of what's going on here. It's very simple. If this is H, right, then you got like this. Here's your H1, and then H2 would actually be all the way over to here, right? And then H3 is just equal to H itself. So it's like kind of going systematically step, 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 and you just keep taking steps until you're all the way out to the end point. You take n orthogonal steps. So do you guys agree with my identity here? See, I just added 0. Plus, minus, plus, minus, plus, minus. Now, the reason for that, the thing that's so cool about this, is if you look at this one here, what is this? Well, let's look at an arbitrary one. So an arbitrary thing here, something like f of a plus h, let's say j, right, minus f of a plus what? H j minus 1, yeah? So what are we really looking at? We're looking at f of a, let's see here, you know, a1 plus h1v1 plus a2 plus h2v2 plus dot 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 all the way out to what? Plus aj plus hj vj, and then you just have the you know, the rest of the aj plus 1, vj plus 1. So that's the first term there, right? This thing. Probably need to zoom in on some of this, Lauren. And then minus what? Like the same stuff, right? Except what? I really should write, curses. I should really write one more in here. Let me fix it. The interesting thing is the j minus 1th one. Let's try to say that again. So the point is they both share the first j minus 1 terms, right? Like this, up to here, it's the same in both. But then past that, we have aj, vj. So, all right, if you look at that, all of the components are fixed in this difference, except for one particular component. There's a change between the difference. See it? The first is the same, the second is the same, all the way out to the j minus 1th component's the same, the j plus 1th match up. The only one which is different is the jth one. So, if you look at this then, what you're looking at is the start of the partial derivative with respect to the jth component. So this is something like the partial derivative. It has to do with the partial derivative of f with respect to xj at what point? It's not at a, it's at what? It's at a plus what? I almost agree with that. J minus 1. See, it's at, yeah. So you have all of the a's, but, okay, so this thing is, we have a partial derivative. I mean, it's not quite a partial derivative yet, right? I have to divide what? I would have to take this, and I would have to divide by h sub j, right? So I would take, I can say this, f of a plus hj vector minus f of a plus hj minus 1 vector divided by h sub j, right? The limit as h sub j goes to 0, right, that's equal to actually partial f partial xj at the point a plus hj minus 1. Yes?
So why don't you divide it by hj instead of hj minus 1?
Because it's the, because that's the, I mean, that when you look at this, it's the h sub j which is being added to the jth component, right? Everything else is the same. So I'm going from nothing in the jth to in the jth a sub j plus h sub j. So as the limit as h sub j goes to 0, these converge, and it's fixed at this point. I mean, this point is fixed. The element which is changing is the jth one. Now, if this is continuous, right? You know what's going to happen as h goes to 0. What happens? Yeah, this goes to partial f, partial xj at a as h goes to 0. Because as h goes to 0, of course, all of the steps leading up to h go to 0 as well. Now, that's not the argument yet, but that's something we should observe. All right. So, how do we convert statements about derivatives to statements about actual changes in a function? what theorem from Calculus 1 is the tool we want to use here? Let's see here. Let me be a little bit more explicit in my fishing. I want us to be able to write f of a plus h sub j vector minus f of a plus h sub j minus 1 vector is equal to, some quantity times h sub j. So what I have here is the change in f and the change in h sub j is equal to some quantity. And I want it to be something about the partial derivative. So what I can do is I can say partial f partial xj at the point what? I could call it, say, c sub j, where c sub j is what? Let's see here. To be more specific, I really want to look at this on the closed interval. The closed interval I'm thinking about, of course, is minus h sub j, h sub j. Let's just suppose h sub j is positive for the sake of not going nuts. All right. If h sub j is positive, then I've got this interval minus h sub j to h sub j. If h sub j is negative, I have the interval h sub j to minus h sub j. Anyway, I consider this closed interval. I have this continuous function, which is differentiable. I can use the mean value theorem to select a particular point in this closed interval, which the change in y is equal to the derivative at the point in the interior of that interval times the change in x. And so c sub j is an element of the open interval from minus h sub j to h sub j. Well, now we have something, right? Because if you apply the mean value theorem to each one of these successive differences, you've connected each successive difference to the partial derivative at some point in the open interval between these particular closed intervals of the components of h, which is pretty awesome. What happens to c sub j as h goes to 0 while we're talking about the setup here? What does c sub j go to as h goes to 0? 0, right? Yeah. Oh, I see my setup is slightly wrong. What should I say? See, this is not right. Where the limit point is where? A plus, right? So I shouldn't have this. I should have what? I should have a sub j minus h sub j, a sub j plus h sub j. If it's bothering you that I assume the h sub j is positive, there's an easy way to fix this to make it generally true without breaking up into cases. Absolute value. That's true. Okay. Here, right? So it's not on this interval we want to use. It's actually on what? A minus the absolute value of h sub j, comma a plus the absolute value of h sub j. Okay. Apply the mean value theorem to select a c sub j in here. And of course, c sub j doesn't go to 0. It goes to where? A, right? A sub j as h goes to 0. Okay, I want to wrap this thing up so we can move on to greener pastures. Let's see here. This stupid thing always takes longer for me to prove than I want it to. It's just the nature of the beast. So what we have then, right, is the sum. So I can apply this result over and over and over and over and over again, right? And I start with the first difference I have. I start with, which is it? It's the So I start at n. And basically, this is at n, and I go all the way down to what? The last one is 1. So I sum I equals 1 to n of f of a plus h sub I minus, I used a j over there. Let me use, let me use technically I fixed j with some other meaning at the start of all this. A plus h sub I minus 1, right? But what did we just work out that is equal to? That's equal to a sum I equals 1 to n of what? Partial f, partial xi at c sub I, what? Times h sub I? Is that right? Yes. So there you go. Now what do we do? We look at the, let's go back to our what we're trying to do. Look at the Frechet quotient, right? So look at delta f minus daf of h over the norm of h. I'll leave the 1 over the norm of h out front to start with. And we've got what? We've got a sum, I equals 1 to n. And if you don't mind, I'm going to just I'm going to look at the two things, and I'm going to just do this step here. So from the delta f, I have partial f, partial xi at c sub I, right? And from the definition, our proposed definition of the Frechet differential for f, little f, I have just partial f, partial xi at a, right? So I subtract partial f, partial xi at the point A. Now there was an h sub I in both of these terms that I'm factoring out to the front. Yeah, it probably should be inside the sum. Sum I equals 1 to n. Thank you. H sub I divided by the norm of h. I can bring the norm of h inside the sum too, just for the sake of. Okay, so we want to show that this limit goes to that the limit of this as h goes to 0 is 0. So this piece goes to 0 as h goes to 0, right? But the other piece, what can we say about, if we have h sub I over the norm of h, what do we have? Let's look at the absolute value of this, right? That's, if we assume that we're working with an orthonormal basis, no loss of generality is found in that, actually. So we have the norm of hivi over the norm of h, right? And that's less than or equal to what? The norm of h over the norm of h. There's where I need that special fact about the basis for v. And of course, that's equal to 1, right? So then I'm just going to appeal to some, I think, common sense. I have a term which is bounded, right? The hi over h is bounded by, its largest it can be is 1. And I have this other term which for each I goes to 0 by the continuity of the partial derivatives. So we showed that this goes to 0, which then shows you that indeed the Frechet differential is so constructed. But this is the kind of argument that's needed to piece together the information about partial derivatives to get the information about the total derivative, the Frechet derivative. Because the Frechet derivative, again, is a multivariate limit, right, which is subtle. But the continuity of the partial derivative suffices to overcome that subtlety. So there it is. Questions? So. If you would like to see the two-dimensional version of this, you can come to Complex tomorrow. All right, all right. So let us move along. Anybody have any questions about math? Ah! Questions about tyrants. I will not entertain questions. I will not suffer tyrants in this class, besides myself. Let's see here. All right. All right. So I think you guys you've suffered enough analysis for one day. I am going to be sloppy, if you don't mind, about the proof of the chain rule. That said, what I'm going to show you is nearly the proof, and I really do mean that. If you look at what Edwards has written in his, obviously Edwards' advanced calculus, what I'm talking about. But the proof in Edwards for the chain rule, when I first looked at it a few years ago when I started teaching this course, I looked at the proof and I'm like, this is awful. This just looks horrible. But then I read it, and it's actually not bad. It's really just fleshing out the details of what I'm about to show you, and it's totally natural. It all goes back to the basic principle of what is a derivative. Why do we differentiate? What's the point of differentiating a function? The point of differentiating a function is to come up with a technique which selects the best linear approximation to the change in the function at the point. So when you look at the question of the chain rule, the question is, what's the best linear approximation to the composite of two functions? All right? And so that has all to do with what happens when you compose linear approximations. And the answer to how you compose linear approximations is very simple. If you have two linear approximations, and again, I'm descending to Rn to stop fidgeting with bases. But if we have functions, if we have two linear transformations, right? Here's the linear algebra of this problem. If I have, say, T1, which is going from, let's say, Rn to Rp, and if I have T2, which is going from, let's say, I don't know, 7 is a variable. All right, fine, 7. No, I can't do it. I'm sorry. It's just not right. 7.
You're not going to use 7 anywhere else in this problem.
Oh my goodness. Oh, that's so horrible. So horrible. Now I've messed it up. So Rp, I'm going to make the first one go from P to N. I don't know. I can never make these stupid things right. What composition makes sense here? Yeah, so T1 of T2? Okay. So T1 of T2, or T1 composed with T2 as we denote, is a mapping from what? It's a mapping from Rm to R, and then so T2 goes here to here. Then you got Rp, and then T1 does the rest of the job over here to Rn by our construction. So this is the composite. And now if these are linear transformations, right? If these are linear transformations, then of course we have T1 is what? T1 is equal to the standard matrix of T1. Excuse me, T1 acting on a vector, say acting on x. T1 of x is equal to the standard matrix of T1 times x, right? T2 acting on y is the standard matrix of T2 times y, right? That's what we mean by standard matrix. But the amazing thing about matrix multiplication is that the composite, T1 composed with T2, what's the standard matrix of the composite? right? It is in fact just the matrix multiplication of T1 times T2. And if you really want to get down to the why we define matrix multiplication as we do, this is why. The reason matrix multiplication is so defined is precisely so that it interfaces with the composition of linear transformations in this way. Now, a more basic reason, if you go back historically, the reason matrix multiplication is defined as it is because of when you solve multiple systems at once, you can talk about substitutions of one system into another. And when you start looking at the coefficients of the respective coefficient matrices, you find matrix multiplication. That probably is how it was discovered first. But there it is. So when you're thinking about the best linear approximation for one function and the best linear approximation for another function, right, you kind of expect that this is going to come into play, because this is how composition works for linear transformations. All right, so let me remind you, just before I do that, let me remind you how it works then. So definition, we have a function from, say, Rn to Rm is differentiable at, let's say, x equals to a, then dAf of h is equal to, well, here's Edwards notation, f prime of a times h. Now, I'm assuming that it's Fréchet differentiable. If it is Fréchet differentiable, then this formula holds true, all right? The converse direction, again, I need the continuous differentiability of the partial derivatives in order to get from partial derivatives to differentiability at a point. I need continuity of the partial derivatives, all of them. All right, but anyway, assume f is differentiable, then this is its breakdown, and this is the so-called Jacobian matrix. So sometimes I will use this notation, Jacobian matrix of f at the point A. And then this is just a matrix multiplication. The linearization, what's the linearization of f? We have f of a plus h is equal to f of a, well, not equal to, but it's approximately equal to f of a plus the, f prime of a times h. Or, if you don't like centering, if you don't like that notation, we also have f of x is approximately f of a plus f prime of a times x minus a. Keep in mind, don't be fooled, that's a matrix column multiplication I'm writing there, as I showed you guys in the example last time. So yeah, let's look at an example. Another one would hurt. Maybe this one with sound would be good. Actually, an example with sound, I hope. There's sound, right? Okay, just checking. Here's one of my favorite examples. F of r theta is r cosine theta, r sine theta. So this is what? Mapping from R2 to R2, right? So what I want to do is just find the Jacobian and exhibit a linearization. That's what I'm doing, okay? So the f prime of r theta is, so what we do is partial f partial r, partial f partial theta. That's the differential on E1 for the first thing, the differential on E2 for the second thing, first and second columns respective. But the differential is connected to the directional derivative. So that's why I have partial derivatives here. Anyway, so what is that? That's cosine theta, sine theta. What you got here? Minus r sine theta, r cosine theta. So there's the Jacobian matrix. Now you guys pick a point where you want me to linearize it. 1 pi? Okay. That's good. I was hoping you wouldn't say 0. 0, that I don't know about. I mean, well, I know about it. I mean, I can do it at 0. It's just, there's something kind of pathological about 0, right? Because the second column is 0, right? There's something really different about this function at 0. Anywhere except for 0 that has 2 linearly independent columns, right? So the linearization is surjective and injective away from r equals to 0. Think about it. All right, so here we go. F of, and which way do you guys do it? I'm going to do it which way? This is the x one? Okay, so f of r comma theta is approximately f of 1 comma pi plus f prime of 1 comma pi times the column vector r minus 1 theta minus pi. Okay, so what is that? Let's see here. F of 1 pi is minus 1, 0. See, because I'm putting 1 cosine pi is minus 1, 1 sine of pi is 0, so minus 1, 0. And then I plug in theta r equals to 1 and cosine equals to pi up in here. I get 1, I get 0, 0, and minus 1. That matrix I have to multiply by the difference vector, r minus 1, theta minus pi. And out pops the answer. So I've got minus 1 plus r minus 1, comma, pi minus theta, which of course I could rewrite as r minus 2, comma, pi minus theta. So there you have it. What'd I do? I was like, this feels wrong because if I'm trying to linearize it around 1, r equals to 1. It's weird that the okay, so what did I do? Yeah. Oh. Minus 1, 0. 0. Okay, so they're both minus 1s is the point, which that's better. So then this is giving me minus r plus 1. The 1s cancel. I'm happy about that. And so we get r. Is this thing okay? Did I mess that up too? No, I already had the minus on that. That makes more sense. So if theta is, no it doesn't. There's a minus, I forgot. I mean, if theta is about pi, then cosine is minus 1 at pi, right? So this should be approximately minus r. The next term in theta is second order, because the power series expansion of cosine theta is 1 minus theta squared over 2. So I don't expect any linear correction from the cosine term near the point. Sine theta, on the other hand, is approximately, well, it's 0 at pi, and the next term in the sine power series is cubic. So, I mean, I don't expect a correction here either. So this is essentially just, yeah, pi minus theta. So at pi, this is 0, of course. Yeah. And there you go. That's the linearization. It gives us the best it gives us a linear approximation, essentially. I mean, it's affine, technically, because there's a constants also, right? It's a constant plus a linear transformation. This is much, much easier to study than this nonlinear function. This has got sine and cosine, right? Those are complicated functions. This just has r and theta, just linearly appearing. So we can take some complicated nonlinear function, pick a point, close enough to that point, if the function is differentiable, we have a good approximation to the function by a linear object.
So
Exactly, yeah. This technique is used over and over and over again in math. Like a lot of time in applications in engineering, you'll have some like complicated nonlinear system, but you know the point which you're interested in. So what you do is you take the problem, you linearize it. You solve the linear problem, and you get all kinds of local information about your problem. That's the idea.
Once you said the purpose of all the circuit analysis courses that they use that nonlinear things that become linear. So
Yes, yes, yes.
Could we like extend that to like the accuracy of that by like adding like a clear term like F double prime?
Oh,
Kind of like doing like whole,
is there a multivariate power series?
yeah.
Yes.
Like we could do that with that.
We'll get to that eventually.
Okay.
But
Is that
I-
all, like, the same general rule?
I don't think I'm so bold as to try to attempt the multivariate power series discussion in here for mappings. I think I just suffice to do it for real valued things. But yeah, this is of course just the first correction term in something more monstrous. But
And like a second one could be like F double prime over 2.
I don't,
So-and-so.
you know, I can't tell you quickly what the next thing is.
Okay, it's not as easy. It's just
Maybe not, yeah, maybe not so easy. Okay, so chain rule. So let's suppose f and g are functions on, you know, Rn and, well, functions, let's say, oh, goodness gracious. I guess I'll stick with my setup. What did I do? Rn to R, what is it? Stop saying 7. Rm to Rp and Rp to Rn. I can never, this is a poor choice in letters. Can I fix it? I'm going to fix it. I'm going to make this N. I'm going to make this M. I like that better. And let's see here. So then if this is G, and this is F, what composition makes sense? Is F composed with G make sense? Why don't I believe it? Oh, you're right. F composed with G. So F composed with G is then a mapping from what? From Rn to Rm, right? Okay, setup. So suppose that F and G are both differentiable in the Fouché sense, right? At compatible points. So what I'm saying is that assume, let's see here, G is differentiable at, let's say, x equals to A, and F is differentiable at, let's say, y equals to G of A, right? Oh, by the way, just as a notation, I was suggesting that this goes, so Rp and Rm, right? I'm suggesting that the variable here is x. So sometimes you'll see this notation, like a little sub x, to say, hey, x is the variable here, and then y is the variable here. It's a nice notation for its purposes. But anyway, so we have f is differentiable function, excuse me, g is differentiable function of x. F is a differentiable function of y, specifically at the point G of A. Then F composed with G is differentiable at x equals to A as well. Moreover, the differential at A of F composed with G is equal to the differential at g of a of f composed with the differential at a of g. When we take the standard matrix of the above, what do we get? So what's this, what's the standard matrix of dA of f composed with g? What's that? That's f composed with g prime of a in Edwards notation, right? So what we get is the following. We get f composed with g prime of a is equal to, what's this? This gives us f prime of g of a times g prime of a. Upstairs, we have composition of linear operators. Down here, we have multiplication of matrices. And this one chain rule will reproduce every single one you ever saw before in calculus. You pick me a chain rule, I will show you how it reproduces. This reproduces it. But at the base of it all, it's because if you take the composite of two lines, the slope of the composite is essentially the product of the slopes of the lines. That's the one-dimensional version of this. But more generally, it's the product of the matrices, which, make up the thing. Here, let me show you a really weird. Should I show? I guess I should show you a not so weird application. Fine. Oh yeah, you could do that for me. I was going to say the proof of this is simply to multiply the linearizations of the functions which is given to you because they're Fauché differentiable. We have linearizations. You multiply linearizations, and you identify that the new linearization, which is formed in this way, it satisfies the Fauché quotient. If you look at Edwards, that's the argument. It's no, we can do an example. I was just going to say I'm not going to prove it. I'm just going to talk about it. Read. It's in Edwards. It's there. So which chain rule would you like me to reproduce? I'm looking for a generic chain rule. An actual function with variables in it is distracting from the point. How about this one? We learned that the derivative with respect to time of f of gamma of t, or let's say r of t, right, is equal to what? So here, f is a function from, say, R3 to R, like a level function. And here's a space curve. So we learned in calculus that what you do is you take the gradient of f, evaluated at R of t, and you dot product with dr dt.